that's going to talk about instabilities of pipe flows. Thanks.
Thanks. Yeah, so I couldn't quite decide what to talk about, but please pay attention to the plurals. You know, it's instabilities and it's flows. Oh. I thought it installed. Okay. Good, good. Oh. Well, if we can't. It probably doesn't obstruct too much. While my talk is being given. But ah, good. All right. Thanks. Let's go back to the first slide. At least I try. No. Okay, I won't touch this. I'll only touch that. Okay. All right. So yeah, let's start. And I start with my sort of usual introduction. So this would just be a Newtonian fluid going through a straight pipe. And I'll talk about other things as well later on. So here, going back to Reynolds observations, you know, obviously we don't have a linear instability for pipe flow. But if you had large enough Reynolds numbers, and if you add a finite amplitude perturbation, you can get these flashes or puffs of turbulence. And I'm just showing some in a movie here that you see what they look like in experiments. And yeah, so Reynolds also observed that if he improved the inlet of his pipe, he would only get transition at far higher Reynolds numbers in sort of more in the fully turbulent regime, where then he gets expanding slugs, supposedly. So clearly when you get transition, when your laminar flow becomes unstable, depends on the details of your experiment. It's not easily answered. But Reynolds actually made a proposition that you could define what he called the real critical value of the velocity, sort of the real critical Reynolds number, let's say, by thinking about the problem as coming from a turbulent flow. Well, he says it in slightly different words, but that's the meaning. You know, if you start with turbulence and if you reduce the Reynolds number, the point where you lose turbulence and where you relaminarize, this is sort of a well-defined quantity. And I just try to tell you in one slide how one can estimate the value of this critical point and why it's not so straightforward to do that measurement as Reynolds proposed it. So what we ended up doing is we looked at individual puffs, and we basically, you can quantify the decay of puffs. So this is in a direct numerical simulation, co-moving frame of reference. If you look at it, it will eventually decay, and the decay is always sharp compared to the lifetime. This would be energy, the turbulent level, and then it suddenly sharply decays. And you can do the statistics on this, and you will find that this is a memoryless process. So puffs don't age, the energy doesn't go down slowly, but they live for long times and then they decay suddenly. So this is memoryless. And likewise, you will find, so this is a decay process, but then if you go a little bit higher in Reynolds numbers, you will see more often that puffs actually split before they eventually may or may not decay. So you get also a growth process going from one puff to two. And the message then that we try to get across, you can now balance these two processes, and it turns out that puff splitting is equally a memoryless process. So the probability for a puff to split is not dependent on the age of the puff. It's always constant regardless of the age of the puff, right? Okay, and then you can do this ansatz here for the decay as well as for the splitting. So these would be the lifetimes basically or the characteristic timescales for a puff to decay that increases steeply with Reynolds number by about 6, 7 orders of magnitude in a small Reynolds number regime. And if you now do the same analysis for puff splitting, you will find that the lifetimes go down very drastic. The times before splitting happens go down very drastically as the splittings happen faster and faster. And now the message of our work back then was that the point where this is balanced, where you have equal probability of a puff to decay or to split, is where you can estimate your critical point to be. Yeah, and seen from far, this actually works quite well. So you see in space-time plots here, time on the horizontal, that puffs below this intersection point certainly decay, and above you get this multiple splittings, and you end up with more puffs than you started off with. So we did this with DNS and mainly experiments. Most of the data is taken by Kerstin Avila in the experiments here for the splitting. Okay, the key question then is, how can we characterize this transition? And our proposition was it's a non-equivalent phase transition, and most likely it's to do with directed percolation. Now, I'm not going to say much about this. I'm just going to show the results, but happy to discuss afterwards. So meanwhile, we did experiments. This is done by Mukund in my group, where we created a pipe with periodic boundary conditions, and we can only do this because puffs are memoryless. Again, I would be happy to explain, but I want to talk about something else really. So where you start with many puffs, this is at Reynolds 2020 shown on the left, and eventually everything decays. And if you are above, so time is going down, if you're above at 2060, above this intersection point, so this is 20 below the intersection point, 20 above, then you keep having many puffs and you get splittings and you get decays, but they sort of balance each other, and you go to a statistical steady state, which has a non-zero turbulent fraction. So here we are sustained, here we decay. Okay, so after 10 years trying to exploit these ideas and trying to get to the point, is this sort of a phase transition, and may it be directed percolation? We got these, what is that, turquoise, light blue points here from the experiments. This really literally took Mukund 10 years to get. Well, we have many of these, but these are the most reliable ones that we could get. And the open symbols are now from a combined, well, it's from a model, but we fed into the model all the pairwise interactions between puffs that we measured in experiments. So it's, sort of a inspired by experiment model. And here, well, first of all, you can see that they match the prediction from the experiments. But what is interesting is this model actually falls into directed percolation. Now, pay attention to this black line here. So this is the scaling range up to there, where you can find the directed percolation exponent, sort of, up to 2042 or so. And we didn't get a single data point from the experiments in this regime. It would take us about a century to get this data point down there that we got in the model after a few weeks. So what I'm trying to say, it's literally impossible to get into the scaling range. The scaling range you only get in very closely, but far enough from the far away enough from the scaling range, we get good agreement between this model and what we actually measure in experiments. So what turned out to be much easier is to look at this in co-ed flow, make it one-dimensional. So we have an actual very short, but azimuthally extremely large setup here. This is not to scale at all. And I hope the movie, well, if it doesn't work, I don't know if I can start it or something happening. Yeah, it is. Okay, so now we have azimuthally periodic boundary condition in the experiment. You see these patches or puffs of turbulence bouncing around, and we can observe it for long enough times. And here we actually get a reasonable scaling range, and we get exactly the expected exponent for directed percolation. So that is just to summarize what we find for the sort of usual transition Newtonian pipe flow straight pipes. 2D, there's various studies who also find directed percolation in channel flow. However, it seems to be quite, at least very unclear, and there's a different mechanism which changes things, which is sort of deterministic creation of streaks at the downstream leading edge of a stripe. So this is for fully localized stripes in channel flow, which makes the things non-memoryless. But this is not what I'm going to talk about. I wanted to talk about additional control parameters for pipe flow. So we stick to the sort of one-dimensional pipe flow, but we add further control parameters, not just the Reynolds number. And I wanted to, well, this is what we did in the past. Actually, we first started these problems always with lifetimes. Lifetimes are a nice quantity to look at, because in a very small Reynolds number range, they increase dramatically, as I said, by 6 or 7 orders of magnitude. So it's supposedly a very sensitive quantities to changes to the problem. And now I'm just, jumping in. I'm mostly going to talk about this case here, viscoelastic pipe flow. So I'm going to talk you through this figure first. The other ones are kind of equivalent. So adding polymers, so the case I told you about is this axis, 0 ppm polymer concentration, Weissenberg number 0. This is where you have this dP, or at least we believe dP transition in pipe flow when you go up here. As we add polymers, you see that these puff lifetimes are moved to larger and larger Reynolds numbers. So you have to go to higher Reynolds numbers to find your transition again. And as you move on this axis, then at some point you're hitting another curve where things change quite dramatically and you get a completely different instability. I'll show you what's different about this instability in the next slides. And in this case, you also get a different turbulent state as a result of it. You cannot do the same thing, just you don't add polymers, but you let your flow pulsate. So you increase your pulsation amplitude, puffs again get delayed, the puff transition, and then you, in this case, you get again a different instability to a helical mode. You can also not do any of those, but you curve your pipe. Also in this case, the puff transition gets delayed. Your lifetimes, to get to the same lifetimes, you have to go to appreciably higher Reynolds numbers, and then you run into a supercritical transition, basically a linear instability intersecting with this. And in particle-laden flows, if you now add particles to it, funnily enough, the puffs move to lower Reynolds numbers. But well, analogous to the other ones, you also get a different transition to a globally fluctuating state without any puffs. Okay, so that's just, as I said, we're going to focus on this one case. I just wanted to show this analogy in different settings. Okay, so what is the difference here? So from experiments we saw here, we have clearly distinguishable puffs on the one hand, but if we go to that side here, to what we called elasto-inertial turbulence or the elasto-inertial instability, and we go up here, we find the fluctuations set in sort of globally everywhere in the pipe. There's no localized structures anymore, and as we keep increasing, the amplitude of the fluctuations increases, but at a much lower amplitudes than the typical spatial temporal intermittency we see here. Okay, it's probably enough for that. Okay, yeah, the other point would be that as we increase the Reynolds number now for, yeah, so if we go up here, it's the same, it's actually also 500 ppm. There's basically no hysteresis. So if you add a perturbation or not, and everything looks continuous, there's no jumps in this. So it looks very much from experimental perspective like a continuous transition, possibly linear instability, but I'll get back to that. And there's been a lot of recent discussion, largely from theoretical perspective, if what's the nature of this transition to EIT, and if it's either subcritical or if it's linked to a linear instability, supercritical, and may even be linked, well, this would be a subcritical version of elastic turbulence, which is known for curved streamlines. Okay, but I don't have time to explain this too well. So let me get back to experiments, what we observe here. So it took us also a number of years to observe any structures close to onset. So this is for different polymer concentrations and actually also different viscosities of our solvent. So, but these are both close to onset for the two different fluids. We happen to find very close to onset these chevron-like structures, even though they remain to be sort of chaotic and never settle down to really a steady state. And the prediction from linear stability analysis, so that would be this very nice study by Garg et al., the group of Shankar and Subramanian, they find actually an analogous linear instability to the chevron type mode. And we were quite happy in finding that in the experiments eventually to have some structural information there as well. Okay, I have to go this way. So does it mean we have a linear instability or not? I told you, well, we never quite settled to a steady state here. If we look at amplitudes of fluctuations close to onset, nevertheless, you know, it looks quite suggestive, something close to a square root. If we now look at this is now a second parameter, which, you know, related to the amount of polymers in there. It's elasticity number, so it's actually Weissenberg number divided by Reynolds number. What happens here is that we move in experiments, our onset goes to really low Reynolds numbers, Reynolds number of 5 or so of our transition, which is not at all covered by the linear stability analysis. The linear stability analysis, I think that the lowest they can get to with certain combinations of the viscosity ratio of the fluid would be some Reynolds number slightly below 100, but certainly not. So this is not of this order. So we are an order of magnitude lower than predicted by linear stability analysis. So this led us to believe that we possibly, even though we cannot distinguish in experiments, we probably still, what did I want to say? Subcritical. Yeah, should get this right. Subcritical. So that even though it looks like a continuous transition, we may trigger by some noise that we have unavoidably in our experiments without wanting to do it. We may always trigger the instability with finite amplitude perturbations. But yeah, it's hard to say from experiments. Okay. So now I wanted to, I have no idea how many minutes we lost at the beginning and how much time I have left, but. Okay, okay. Now I wanted to talk about a second aspect of this instability, but now not looking at this sort of low Reynolds number, high polymer concentration, but rather coming more from this side at the high Reynolds numbers, where this is very well known as a phenomenon of polymer drag reduction. So if you start with fully turbulent flow here on this axis, and you increase your polymer concentration, this is a great way of reducing the drag in your flow. And this has been known since 1950s or late 40s. And what Work found around 1970 is that as you increase, so this is Reynolds number, this is the friction factor in the pipe. As you increase the concentration of polymers, you get stuck. So you reduce from Prandtl Karman your friction factor, but you don't quite make it to Hagen-Poiseuille. Instead, you get stuck of what is now called the maximum drag reduction or the work asymptote. Yeah, and now we're going to take a cut here, starting from turbulence, going across, increasing the polymer concentration. All right, so let's do that. So first we take a cut up here. So this is now where our two instabilities meet, and we stay above this. And if we do that, so, okay, not surprisingly, at 0 ppm polymer, we are directly on Blasius or Prandtl Karman, if you prefer. It's not too far off for these Reynolds numbers. Then we increase polymer concentration, we reduce our drag, and we end up on the maximum drag reduction asymptote. Exactly as expected, I could add more polymers, wouldn't change a thing. Now we take a more interesting cut. We go across here. And we again start on Blasius, we increase, oops, going too fast. So here we go from sort of a fully turbulent fluctuating flow back to localized structures. So I believe these are puff-like structures, just we look at pressure fluctuations, it's not so easy to identify, but certainly spatial temporal intermittency returns, and then we relaminize completely. What should not happen at all according to sort of the traditional picture of polymer drag reduction. Until we go to even higher concentrations, we have another instability which sets in globally, like elasto-inertial turbulence happens to do, so we don't get localized structures. And then we end up on the maximum drag reduction asymptote from below. Okay, so a last slide on this topic, at least I believe it's the last slide. So this is what elasto-inertial turbulence looks like far away from onset. So at onset, we had this chevron structure. Higher up, we get more like a wall mode. I could show you this transition as well. But anyway, you kind of see that the streaky structures here that I'm plotting are much, the highest amplitudes are closer to the wall. And this is now below 2000 elasto-inertial turbulence. And this is at the rather high Reynolds number, I think 10,000 for maximum drag reduction asymptote. And these are spectra we measured. So these are all spectra, different Reynolds numbers below 2000. And we were comparing to, I mean, I'm not claiming we have a minus 5/3 scaling. I just put a minus 5/3 line here. And this is Reynolds 11,000, what a typical turbulent run would look like at this Reynolds number, the spectra. At EIT, we have something close to a -3 scaling, even though, you know, not a huge scaling range, but certainly it's steeper than minus 5/3. And this is now for MDR at much higher Reynolds number. We go up to Reynolds 40,000. And you see that on MDR, you also happen to be much closer to -3. Again, you know, it's not huge scaling ranges than we have here, but it's clearly steeper than in Newtonian turbulence, and it seems to match quite well with the EIT at low Reynolds numbers. Okay, so I have one more thing I wanted to mention after this, but let me conclude about here first. So yeah, so if we just look, you know, at Reynolds number, then we believe that pipe flow falls into the directed percolation universality class, and we have this transition where we can define a critical point where turbulence sort of coming from above stops to or becomes transient and decays. Then we get different instabilities as we add additional control parameters. And the one I mostly spoke about is then this one to elasto-inertial turbulence, this instability, and which can happen at very low Reynolds numbers, so of order 1, if you go to high enough Weissenberg numbers. And this happens to arise from a mode predicted by linear theory, and there may be a connection to the maximum drag reduction asymptote. And before I conclude, I guess I still have 1 minute, or? You have 1 minute. Okay, good. Now, this is something we looked at much more recently, and this is back to Newtonian pipe flow. So this is plotting the deviation from with respect to the Blasius friction factor scaling in experiments in DNS, and you see we are perfectly on Blasius. This is what Prandtl-Karman would predict, until about a little bit above 60,000, where we start to deviate from the Blasius power law, and we go somewhere closer to this logarithmic prediction. And if we now look at the correlation, well, it's mutual information, but let's call it a correlation between deviations in friction and large scale motions in the log layer, then we see this very nice onset, and we're adding points to it as we speak. Unfortunately, each data point takes about a month, and the last one, well, either way, it takes a long time, but you know, this is sort of, to me at least, suggestive that there may be some kind of transition happening within the flow, which is something interesting we may spend. Somebody was asking what we do the next 10 years. I don't know if I spent 10 years on that, but you know, I just want to put this up for discussion also because Ivan and Beverly are here. So I would be interested to discuss this further later on, but let's go back to the conclusions. Thanks for the attention.
So is there shear thinning significantly going on with your polymers?
There, to a certain extent, yes, but I wouldn't say hugely so. So we characterize this. Now, it's in the supplementary information of the PNS paper. It was a less than 10%, I believe. It was a few percent in this, shear ranges that we covered. So yes, but it's probably not the predominant factor. But okay, sorry, the microphone is back there.
Bjoern, could you please go back to the slide where you were doing sub and supercritical?
So, sorry, which one? Say it again.
Just go back.
Okay, you
I'm
said
doing
stop.
Lorette here. You overshot.
This one?
No, super and subcritical. Yeah, that one.
Yeah.
Do you remember the beta value for this, for that solution?
It will be, somewhere between these two cases. Let's call it 0.5.
Okay. And what are you plotting on the left-hand side?
Thanks. On the left-hand side is the fluctuation in pressure that we measure.
Point-wise.
Too close to each other points in the pipe, maybe 2 diameters apart. We have a differential pressure measurement, but it's about 2 diameters apart. And yes, it's normalized in some funny way. Yeah.
Okay, there was another hand I saw up here.
Mike, I think
I'll ask a different question. Alexander, so again, on this slide, you made a comment that it looks superficially like you have a supercritical linear instability, but then you made a comment that you don't think that that's the case.
Well, I don't know.
Okay.
I should say I don't know. I mean, if we settle to the steady state here, or I think is it a hop? Well, I don't know. If we settle to this state, I would be making a very definite point here. But since we of course try to get closer and closer to onset, but it never settles to something really steady. So all I'm saying is, from experiments, it will be extremely hard to decide if this is super or subcritical. This is all I can say.
Okay. So in our simulations in channel flow, not pipe flow, and beta's closer to 1, we see that even in the linearly stable regime, incredibly small amplitude fluctuations go to something non-laminar,
right?
Which would be consistent.
Yeah, no, that would be very consistent. Thanks. Yeah.
So maybe I can talk about a few of those papers on there that looked at the bifurcation, and it's very subcritical. And the lower branch as you're going back is very small amplitude. Yeah, so it'd be very easy to just be above that and then look as if it's unstable. So I think that's probably what's going on there. Well, I mean, we talked about it in the past. I bring it up because Mike's brought it up.
And of course, the other key question is that even I guess, discussed at great length is, this prediction of Aldroyd B here, that we can only go down to Reynolds, whatever, something like 60 or so. Do we really have this sort of quantitative level of comparison between polymer solutions and Aldroyd B? So, I mean, if yes, then I would say, okay, we must be subcritical here, but I don't know if we have. So, yeah.
Yeah, but Aldroyd B is more likely to give you instabilities when you have stability in reality.
Yeah. I mean, even with P simulations, I wouldn't, qualitatively, everything looks very consistent, of course, but quantitative comparison is still a challenge, right? Yeah.
Okay, I think we need to end it here, and thank Bjoern once again. Thank you. And Rich, should we have half an hour tea anyway? 25 minutes.